Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. Now, if you have any questions throughout the session, if you're joining us on Zoom, just look at the top of the bottom of your screen, wherever your Zoom controls are. You should see a Q&A button. Click on that, type in your question, hit submit, and I'll get to those at the end of the session. If you're joining us on YouTube Live, just find the live chat wherever it happens to be on your device, type in your question, and we'll get to those at the end of the session as well. So my name's Jason Gabrinas. I'm one of Snap-on's national diagnostic technical trainers. Been in the training department the last 9 years or so, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep with Snap-on. Got about 30 different Snap-on franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before that, it was 8 years at Subaru. So I was a Subaru technician in a dealership, and over time, I guess, just became the diagnostic guy in the shop. So always ended up with the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird problems that would show up in my bay. And before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is component testing and correlation. And the correlation part, I think, is most important about this, because we can test components single channel, but when it really starts bringing things to light is when we start adding additional channels to that first channel and seeing other aspects of what's going on underneath the hood. So that correlation between channel 1 and channel 2, or voltage and amperage, or pressure and voltage, or what have you. So we'll talk about a few instances where you're going to see that, where you're going to run into that, and how that might help you in your day-to-day diagnosing. So let's think about, first get back to basics. Why do I even want to do component testing in the first place? So we think about a computer, vehicle's computer. Let's think of it like a house. It's got a front door. It's got a back door. Coming in that front door is going to be all of my inputs. So my NOx sensor, my oxygen sensor, my coolant temperature sensor, all these inputs go into the computer. Then the computer is going to process those signals, however it's programmed to do so. And that's a pretty key point right there as well, because it's only as good as its programming. That's why we have these things called reflashes that happen every once in a while. But based on its programming, it processes that data, that information, allows it to help drive the vehicle down the road. And then it also takes that processed data stream, spits it out the back door. And then that's what you're viewing with the scan tool, that processed data stream coming out the back. So when we're testing components, usually we're going to be testing it before that signal even gets to the computer, just to make sure that the signal itself is good and the component itself is good. And then we don't have a problem in the wiring harness somewhere in between or something like that. For just relying on scan data, we're really only doing half the job. We're only looking at that data after the computer has already got its grubby little hands on it. And I'll tell you what, scanners don't lie, they get lied to, is a phrase that one of my friends said. And I think that's true. Your scanner is only going to tell you what the computer's telling. And if the computer's wrong, that might lead you down the wrong path. And that may have happened to you before. There's a lot of different reasons the computer can do that. Maybe the computer just gets confused, or one of its inputs is bad. But we need to understand where the problem is. Is it internal in the computer? Is it one of the sensors? Is it somewhere else? So that's where this component testing and the correlation come into play. So the component testing really has to do with a scope. So why do we start using lab scopes in an automotive setting? Because in a lab setting, hence where it kind of came from, analog scopes were used in lab settings and electronics for years and years. But they started using scopes in an automotive application because multimeters do not react fast enough to computer-controlled circuits. And these sensors that we have nowadays, the electronic computer-controlled circuits, they don't react fast enough. They don't have a fast enough sample rate compared to what a scope will offer you. So it's the sample rate is how many times per second the tool reads the signal. So back in the 80s and early 90s, so think OBD1 vehicles, a 500 millisecond glitch wouldn't have bothered a car in any way. You'd be driving down the road and lose a coolant temperature sensor for half a second. That's 500 milliseconds. Lose a temperature sensor for half a second, car would have no idea anything even happened, because the car wasn't looking at that sensor at the time, because they have a sample rate too. On the computer has a sample rate. So judging by how often it samples the signals. So 500 millisecond glitch, I could lose that signal for half a second. Car wouldn't even know anything happened. Keep on going down the road. Today, a 500 microsecond glitch can screw up a car. So if we think about 500 microseconds, that's 500 millionths of a second. Take a second, divide it into a million little pieces. Take just 500 of those. That's all it takes. Actually, it's less than that, really. Just tens of microseconds, if that. Because computers on vehicles have come a long way, and they're considerably faster than they ever used to be. So we need to have a high sample rate tool in order to find these short microsecond length glitches. I'll give you an example of what we're referring to here. So the top part of the screen is oxygen sensor voltage, reading data PID, process data coming out the back of the computer. This part of the window down here is a scope hooked up to the same oxygen sensor, reading the same voltage at the same time. These two red boxes show the same amount of time passing. And I think you'd agree there's a huge difference in the way that those two patterns look. So according to the scanner, if you were just using the scanner, you would not have seen these two little dropouts that happen there. Now, it may or may not be a problem with the car at that point, but seeing those two little dropouts, yeah, maybe it was a problem. If I was just using the scanner to see it without testing the component, I would miss that. Now, it's not really the scanner's fault, it's more the car's fault, if you think about it. The car's got the computer in the car anyway. It's got to sample that data, input, process it, send it to the scanner. Sample the data, process it, send it to the scanner. Every time it does that, that little round trip where it processes it takes a little bit of time where it's not looking at the signal. So every time that happens, you lose that resolution, and therefore we lose some information. Looking at it with a scope, we're seeing it live as it happens, coming right off the component. So we are able to catch these little things. It's like watching a 4K ultra high def TV versus like one of those tube TVs you might still have in your garage. Right, big difference in the detail level of what we're able to see, and being able to catch those little intermittent glitches. It's going to save us some time in those comeback and intermittent situations. So we think about comebacks and intermittents. In my mind, those are the two four-letter words that we have when it comes to diagnosing vehicles. Comebacks are no fun because I don't like working for free, and I don't think you do either. And then intermittent problems are the ones that happen on the third Thursday of the month under a full blue moon, and that dog is waving his tail over there at like 53 hertz. So it only happens once in a blue moon, and those are really hard ones to catch because they happen within a fraction of a second. So we need to be able to catch that. The key point is we want to verify. Always be verifying the problem, and then we're going to verify the repair after. Because remember, the scan tool only shows us the effect of a problem after that data has already been processed. It's a good clue. It's going to point us in the right direction. It's going to show us where we need to look, where we need to go, but it's still only the effect. We want to verify that problem and verify the repair. Let me give you an example. Say you get a car comes in, it's got a P0102 code, mass airflow problem. So you go through the flow chart and say, all right, well, I went through all these things and this, that, and the other, and I guess according to this, it needs a mass airflow sensor. So you call up the parts store. Parts store says, well, you say to the parts store, well, I need a mass airflow sensor for this car. And they say, sure, I got it in stock. Maybe. We know how a parts situation can be right now. Hopefully they do have it in stock. And let's say it's $300. So they send it over. You put the part in the car and you send it on down the road and you say, oh man, I really, really hope that car doesn't come back. I hope I got it right. How about instead of crossing our fingers and hoping that we got it right, how about we test the part first before we condemn it? So if I test that mass airflow sensor and it fails the test, it is not working properly, then I can be a lot more confident in my diagnosis when I call the parts store. Then when the new part comes in, before that car leaves your site, test the new part. And you might be wondering, well, why would I do that? And I'll ask you, well, have you ever gotten a brand new part in a box that didn't work? Happens all the time, right? So if we're testing the part first, we can verify our failure. And then if we test the part before it leaves, then that'll help us verify the repair after the fact. And that'll cut down on the comebacks. It's not going to 100% eliminate them, to be sure, but it'll cut down on those type of, oops, I didn't test it first. And also intermittent problems too with the high sample rate. So what is guided component testing and how does it help you? So we talk about the scope And if you have a snap-on tool with a scope, it also has the module called guided component testing in it. So that is the scope, just way, way easier to use than any other scope. It gives us operations, location, connector views, tech notes, and between 1 and 6 testing methods on whatever we happen to be testing. By giving us all this information all in one place, doing a lot of the setup for us, and we'll walk through a couple examples here, it's going to help us avoid unnecessary parts replacements because we're testing and verifying first. Due to that, it's going to help prevent comebacks. And it also helped prevent those never comebacks. I think those are worse. What's a never comeback? Well, it's the car that you diagnosed, you got it wrong, and they said, well, forget that. I'm not going back. I'm just going to go to a different shop and see if they can fix it. And of course, maybe they do at that point. And then at that point, you have lost a customer, which brings us to the next one, helps prevent a loss of customer. Other side of that coin, though, maybe you end up being the shop that gets that car that was misdiagnosed somewhere else and you diagnose it right the first time. Could help attract new customers. You get that reputation out there that, hey, I'm the shop that does it right the first time. And then, of course, overall, all of that rolls up to help the shop's profitability. It doesn't matter if you're the owner, the manager, or the technician. You want to have a profitable shop because everybody can get value from that, right? So all in all, it will help you out, whether you're a tech or a shop owner or a manager or whoever. Being able to verify that problem first is going to go a long way to help you with that. So when we're using component testing, we're checking for failures, generally speaking. So really, when we talk about failures, I think they fall into these 3 main buckets. Right? It's going to be opens, shorts, and a resistance problem. So an open could be no voltage to the component. So my power supply, my 5 volts, my 12 volts is not getting there. Or I have no voltage coming back from the component. So the power supply is okay, but the signal wire is not making it all the way back to the computer. Or we could have a short, excess voltage. So it's a 5-volt reference signal and it's shorted to a 12-volt line. So now it's getting excess power, too much, short to power. Or insufficient voltage, where I have a short to ground. So it's pulling away some of that voltage. So I only have half a volt instead of 5 volts or what have you. And then, of course, we have resistance, corrosion, damage. We think about a multi-strand wire. That multi-strand wire will still have a connection even if it has 1 strand left and all the rest of them are worn out, rubbing on the side of a block or something. They will still have the same ohm reading if I were to ohm it out with an ohm meter, but it will not be able to pass as much voltage and amperage through. So that could be a high resistance problem there. Or, of course, the fun green fuzzy stuff that shows up when we have some sort of water get in there or something like that. So why would I use multiple channels? If we're thinking about testing, by using multiple channels on the same time base, which is key, you can see relationships between multiple signals. I actually got a question on this again this week. I usually get one every couple months. It's like, well, why can't we change the time by channel? And I would say, why would you want to? Because then it's going to throw off all your correlation. If I have a 1-second sweep on this channel and a 5-second sweep on this channel, I can't really see where anything correlates with each other, which is the whole point of using these multiple channels on the screen there. So that's why all snap-on scopes have 1 sweep time across all channels, so we can do this correlation and have the understanding of, well, when this happens, how does it relate to this, right? That's why we want to have multiple channels on the same time base. And you can see those relationships or correlation, as we say, between the multiple signals. So first example I'll give you is going to be a fuel injector. So in a fuel injector, when we can test it electrically, we can check it mechanically, and we can check it hydraulically. All right, electrically, we're going to verify the circuit integrity, make sure the voltage is flowing, which also helps verify the component is even operating. And also check it mechanically by viewing the current flowing through it. So that helps us verify the mechanical motion. So we could have voltage going to it, and the voltage and ground could be okay, but if it doesn't open, we can see that with the current flow. If the current doesn't flow through, it's not going to open. And then hydraulically in this case as well. So we could hook up a pressure transducer and look at the pressure change or pressure drop anytime it opens, which helps us also verify the state of flow of the injector. So here's just an example screenshot from 2 channels. Channel 1 is voltage, channel 2 is current. So on a standard gasoline fuel injector, which is what this is, most of the time, they will be supplied constant battery voltage or alternator voltage, as it were. And then it will, to turn it on, it will be grounded by, we pulled to ground that circuit by the injector driver inside the computer. When that voltage comes down to zero, that indicates that there's voltage flowing through the circuit because it's pulled it down to ground. And then my current should flow at the same time. So we see at the same time, this one goes down, this one goes up, as they should. As the current rises, the current will rise, or should rise, nice and smoothly until it finally fires. When the injector fires, we get this bump right here. So voltage comes in, PCM grounds it. This low point right here, point to point, is going to be my on time or commanded on time. It's how long the computer grounds it. Internally on a fuel injector, it is a solenoid. So we have windings in there, electromagnet, and that electromagnet pulls the pintle off the seat so it'll spray fuel. As it's holding it open, it's going to collect all that voltage that's flowing through the circuit, and it has to go somewhere when it closes. So when it closes, that's why we get that spike in the voltage. And then as we see, the amperage goes up, and then there's a little dip right here. This dip is the point where that pintle actually leaves the seat, starts spraying fuel. So we have to charge up the coil down here. Then we have to get it to start moving. Then when it does finally start moving, the resistance drops for a little bit just because it started to move. And then we see that little dip. We can actually use this to aid in our diagnosis too. If it's opening at roughly the same time, we're mechanically good inside. If it's opening here, there, everywhere, and kind of moving up and down the ramp, that could indicate a bad spring inside. Also, if it does not ramp up smoothly, that current ramp, if it goes up sharply and then over, that'll indicate a problem in the windings of that injector as well. And then, of course, when the voltage leaves the circuit, the amperage should leave as well because they follow each other around. And then we can also see in this pattern, there's another bump right there. So that is what they call the coil oscillation, or the that's actually when the pintle snaps back closed and it stops spraying fuel. So if we look at both of these on the same screen, we can see where the injector opens and the injector closes at the same time. So that's an injector. And these are going to be high-level overviews because we have other way more detailed classes on these individual items we're going to talk about. Just kind of high level and show how the comparison can help us out. Next one's going to be CAN. I have to use really two. Well, I don't have to, I suppose, but it's going to be a whole lot easier if you do use multiple channels when you're checking CAN. So we think about CAN. It consists of two twisted wires with a transmission rate of 100 to 500 kilobits per second. There's also some newer versions of CAN that get up to 1 megabit per second, which is twice as fast. CAN uses what we call a 2 to 2.5 volt differential. So the voltage differential is what we're talking about. You will see on the pattern, we'll talk about it a little bit more. But one signal circuit is identified as CAN high, and the other one is CAN low. At each end of the data bus, there's a 120 ohm termination resistor between the two circuits. And what that is, that acts as a stop sign. So my two circuits go in, and when they see that 120 ohms, they know, okay, well, here's the end of the line. I need to make a loop. So when we're looking at CAN, we're actually looking at a loop. And let me show you the picture. So there's my CAN high on the top. There's my CAN low on the bottom. CAN high goes out, transmits, and then CAN low receives. And due to the crystal clocks inside the computers and all that, they line each other up, and everything's in time when it transmits both out and back. So we can use this to analyze the signal and see, is it in good working order and what's going on. Now, we'll get a little bit more in depth when we go live on the tool in a minute. But what we want to see is we want to see a flat line around 2.5 volts. When it transmits data, which is going to be all these boxes right here, these are the data packets. When it transmits data, the high side goes up by about a volt, volt and a quarter. And then the low side should go down by about a volt, volt and a quarter. It should be the same on both sides because, as I said, we're watching a round trip. So one's going out, one's coming back. CAN problems can be a huge issue when it comes to communicating with a vehicle. It can cause all sorts of other issues. You'll see a lot of those U codes. You know, we have the P codes, the B codes, the C codes, and the U codes. The U codes are for the network problems. So if a module goes down, you'd actually be able to see that in the network pattern because you might get some noise, or you might get a short to ground, which would be down here, or short to 5 volts, which would be up here. You can see any shorts or problems with the line just because of where this voltage falls in a known good pattern there. And as I said, we'll talk about that a little bit more in depth when we go live on the tool in a minute. And also cam crank correlation. This one's pretty popular nowadays because you can find out, do I have a stretched chain? Do I have a timing belt that jump? Do I have a problem with my variable valve timing? So that's a good way to tell. So this is a crank sensor. In this case, it's an analog crank sensor. It puts out, there's 0 volts right in the middle. It goes up to about, in this case, about 14 volts down to about negative 10 to 14 volts. So it's on either side. It's an AC type sine wave is what we're looking at in this particular case. We want to add additional channels. I'll just come down here, add additional channels. I have 2 channels now. So this is on a Subaru with the crank sensor and 2 cam sensors. So we can see there's channel 2, there's 1 cam sensor, and there's channel 3, there's another cam sensor. Now this is on a Zeus, it's got 4 channels. What if I did not have 4 channels? Other tools like Modus or Triton, that's okay. You can still do 1 at a time. So I want to do the crank sensor and the cam sensor at the same time. And we can see how we have this gap in the crank sensor pattern. We can see how that lines up with the blip or the spike there in the cam sensor pattern. And then we have a double gap, and then we have another gap where it lines up again. So this is actually a known good patterns on a known good vehicle. And we can find those known good patterns on our information system. But this is just how I would use that. Okay, does it fall where it needs to fall? And in this case, on this car, it needs to fall between this area here and this area here. It needs to be somewhere within that window of time. And it was. So that means its timing is good. Here's just another example going to the extreme. So we got 4 channels here. We got the crank sensor is the yellow one. 1 cam sensor is green. The other one is blue. And then we also have it triggered on a fuel injector, so we know what cylinder is what at the time. So we can see that that's cylinder 1 fuel injector. So 1, 3, 4, 2 is the firing order, then back to cylinder 1 again. Now also there's a lot going on here, so I want to be able to organize this a little better. On the 4-channel tools, we can also organize it so they're on top of each other, so they're not blending together and melding together. All right, so that's just another thing that we can do. And then how about who failed first? This one was kind of interesting. This is a truck that we were dealing with. It's actually kind of an old truck, 1991. So that's what, 31 years old. 31-year-old truck, 91 Ford F-250 with a 351. Being a 30-year-old truck, it has a distributor. And the problem was it would stall intermittently. And they said, well, we replaced the ignition control module on it already. It's just a little 6-pin module that goes underneath, plugs into the bottom of the distributor there. And well, we said, okay, well, it's stalling and it's randomly stalling. It's not just at a time. It could be running for a minute, could be running for an hour, could be running for 20 minutes, could be 30 seconds. Doesn't matter. It'll stall when it wants to. So we said, all right, so we got to figure out, why is it stalling? What signal goes missing? So this is really where a scope comes in handy. So we can see on the ignition control module, which is where we're testing here, it's a nice easy access point right in the front of the engine. We have the crank signal, or they call it PIP, that goes to the ignition control. We have spout on number 2, so that is spark out from the control module. So that is tells it whether to advance or retard the timing. IDM it may or may not have, so if it does computer controlled well. Run circuit, so that'd be power. Ignition coil negative, so that's the coil control circuit, and then ground. So you said, all right, so we're going to hook up a few channels. We don't need to use them all, but I want to hook up to the crank sensor because I want to see if we're losing the crank sensor signal. We're going to hook up to the ignition signal to see if it's losing the ignition control to turn the coil on or off. And then I want to check the spout to make sure that that signal is getting back in from the computer to tell the ignition control module when to fire. So we took it, we recorded it with these channels, and sure enough, not too long after, maybe 30, 40 seconds, it stalled. So we were pretty excited. We were able to catch the stall while recording. That was pretty good, but where did it stall and why? So we zoomed out on the picture, and I think it's pretty clear to see which one fell out first. Pretty clear that the ignition control fell out first. And if we zoom in a little bit closer, we can see there's the end of the ignition signal, and then there's the end of the crank signal. That's where the engine actually stops spinning. So at this point, you can see, well, I lose ignition signal here, I lose spark, and then over time, slowly but surely, they get longer and longer, which indicates it's slowing down, and then finally it's stalled. Now that looks like that's a whole lot of time. From here to when it stalled, it was a little over half a second. 594 milliseconds was not a long period of time at all. So half a second from here to here, but that is plain as day. Plain as day. You can see, oh yeah, the signal isn't there anymore. Now, even if you were just looking at this and you didn't even know what it was, you could say, well, that ain't right. Because these two are there and that one isn't. Why is that one not there? And then you could understand, oh, that's the coil control, and yeah, that's why it's stalled. But that's the beauty of being able to use a scope to look at pictures, see a visual representation of what's going on, and being able to correlate between, okay, there's the crank, and there's the ignition, and there's the spout, right? So we can see all that, and that just makes it so much easier to see. So we say, yeah, it needs another control module because it wasn't outputting the ignition. So there you go. And then we also have another one we need multiple channels to do. It's going to be on the brushless fuel pumps that we're finding on cars. Because the way a brushless fuel pump works is a lot different than a normal brushed fuel pump that we would see out there. So on a brushless fuel pump, it is going to have the magnets move and the windings stay stationary, versus on a brush pump, it's the other way around. On a brushed pump, the windings move and the magnets stay stationary. So it's kind of the opposite. And the way it works is we have pairs of coils. So you see we have A, B, and C coils, and they can change their polarity, positive or negative, to push and repel against those magnets that are on the rotor, and that's what makes it spin. So here's just one magnet here, but here's a better animation there. So we see the blue is the north and the red is the south. So right now, let's look at this one. This one's off, and now it's on. So the south has gone past, so it's repelling that south around. Then when the blue comes around, it's going to stop for a minute, and then the polarity will change backwards. So now it's a blue polarity, and it's going to repel it around. So as it goes through the motions, it's able to repel those magnets, and it can spin it up to quite the speed in order to get those to spin. But how do I look at it? Since it has these three pairs of magnets, or these three pairs of windings, I need to be able to look at least three things on the screen. So here's just how it controls it. So here's the fuel pump control ECU there. We got ground, we got power, and then we got the fuel pump control signal from the computer, which is just a data line. And then we see it hooks up over here to the fuel pump itself. And we have what we call V, U, and W. So those are those three pairs of coils, and then the ground there as well. We need to be able to see that. So in this case, we would need to see 3 channels at a time. And we can see we have a positive side and a negative side. So when polarity goes up, we see an up. And then when polarity goes down, we see it down. And that's just 2 times through. So positive polarity, negative polarity, positive polarity, negative polarity. And they are 120 degrees offset because of a 360-degree circle. Split it into 3, you get 120. And then we can also see the amperage go through the current flow. We get positive current and negative current. So this one I needed 4 channels in order to. You could do 3. You could just do 1, 2. You could do voltage and current if you wanted to. You wouldn't be able to compare the different magnets or the different windings to each other. You had a 2-channel, but you would still be able to see two or more things. But being able to see that all on one screen is very helpful as well. For more information on brushless fuel pumps, please watch the brushless fuel pumps or the fuel pump class that we did last year. That's definitely worth your time for that. So let's go live. And we're going to do it a little bit different than I usually do. Here, if I get this darn thing to turn on. Because I have my Triton here, which has 2 channels. So we're going to walk through a couple examples using my demonstration board and this Triton. This is going to have 2 channels. So first off, I want to go into my guided component test module. So we're going to click on that. And before we go anywhere, before I ID my car, before I do anything, you'll notice at the very top of the list, it says classes. So this recently got moved to the top of the list because before we used to have to scroll way down until the very bottom to get to training and classes. But now at the top, it's just called classes, and it's right there, right at the top, nice and easy to get to. So if I click on that, you'll see I have three categories. I have power user test, features and benefits, and how to. So if I go into power user test, which is the first one right there, say current probe test, transducer test, and dual channel test. So if I go into dual channel test, you see I got CAN bus, cam and crank relationship like we talked about, EGR solenoid versus position sensor, solenoid and diagnostic switch, flex array bus, which is another 2-channel bus, injector versus oxygen sensor, NOx sensor and EST, mixture control, dwell and O2 sensor, pre and post oxygen sensor. That'd be a good one to do too. Throttle position sensor 1 and 2 on a drive-by-wire vehicle. It's got 2 throttle position sensors, 2 accelerator pedal position sensors, and you want to see how those compare to each other. Wheel speed sensors. I can do 2 at a time on this too. I can do 4 at a time on a Zeus, right? So we have all of these options. Now, these are generalized tests that we can do, really set up for most situations. If you want to get into vehicle-specific testing, we'll go more into a vehicle here in a minute. If I back up, there's also a section on how to as well. And there's 65 different categories of classes in here, from basic electronic component classes through, let's see, EVAP emissions classes, 4-wheel steering class, priority lighting, compression ignition engine preheating class, mapped cooling systems. Those are becoming pretty popular. Selective catalyst reduction, et cetera, et cetera. So 65 different categories of class in there. And this is before I even get into a car. I have this on tool built in training at my fingertips, and that's very, very handy. So if I back up to my vehicle screen, this is all VIN specific information inside the guided component test. So there's over 5 million tests in there. It goes back to 1981, covers most of the vehicles that we currently cover in the scanner software. So in this case, I have a BMW demo board here. So we're going to go into BMW, and it's a 2012 328i with an N52KP engine. And hit OK again. There we go. Once you load into a vehicle, you can see all the systems that we can test. So in this case, we want to go to the engine system because I want to go and check cam and crank correlation on them. So you can see all the different things on the engine that we can test: active grille shutters, engine cooling fan relays, fuel system, throttle control system, etc. But in this case, I said I wanted to do cam and crank correlation. So we'll go to the crank sensor. That's the 4th one down there, CKP. On every component, there's component information. So we'll go in there. And you can see here's how it operates on the top. So it's a Hall effect type sensor. It's located in the left rear of the engine block below the starter motor. Crank sensor is used for misfire detection. And then there's a look at the connector view and what the colors on the connector are. If there's an alternate test location, it gives you that there. So in this case, the ECM. And at the bottom, it says, whoops, I went too far. Back up. Best test location is actually at the PCM. Highly recommend breakout box for testing. They are small because the component location is mounted on the left rear of the engine block below the starter, as they said. You must remove the intake manifold to gain access to the crank sensor. It's very difficult to access. So instead of pulling the car apart, you're going to want to go back to the computer. And then at the bottom, we have more tech notes down here. It says it's torque to yield. You need to do not reuse the bolt and make sure you torque it correctly. So if I back up, everything else here is a test. If I see a signature test, that's usually where I gravitate to because you can tell a lot about a component by looking at the signature. Scroll down a little bit, you can see my connector views here again. Here's where I need to hook up. And then all the way at the bottom is going to give me a known good pattern as well. So all I have to do is hit view meter, doesn't matter which one. You hear it click on my microphone perhaps, and that is the voltage and the time base setting themselves up for the signal automatically. I don't have to know what my voltage needs to be. I don't need to know what my sweep time needs to be. The computer is going to, or the tool is going to set it up for us automatically based on a real vehicle and what we would need to see. So in this case, we got 10 volts and we got 20 milliseconds on the screen. And if I were to scroll this back stuff up, I can have my known good pattern on the screen right there. Now, other than the fact that the pattern is upside down, and that is the signal generator's fault, not the known good pattern's fault. So known good patterns off a real car. Signal generator, for some reason, puts it out upside down. I know. But we can see and compare, okay, that's that, and that's that. Looks good to me. I could even stop it just so I can get one of those gaps on the screen. There we go. So there's a gap there. There's a gap there. Looks good. Actually, I think it even tells us. As RPM changes, frequency of signal will change, but min-max voltage will stay fairly consistent. So there's my crank, but we want to do crank and cam, right? So I'm going to go back to recording again, and I'm going to add a channel. So in order to do this, now if you're watching, I apologize, my face is going to cover it, but on the far top right-hand corner of the screen, there's a graphic that looks like 4 arrows, a little icon. We click on that, makes it full screen, also brings up this information panel at the bottom. So if I want to add another channel, all I have to do is go over here on the left where the eyeball is, click on that green eyeball, turns it on. Next one's probe. That's going to tell me what probe I have hooked up to it. We're just going to leave it as a voltage probe right here. And then we have scale over here. So scale is going to change what the vertical range is. So in this case, it's set to 20 volts. This is also a 5-volt signal. I'm going to set it down to 10 volts again, just like the other one, just so we can compare on even footing there. And then we also have our sweep time. Looks like the sweep time's okay. But if I wanted to change it, I can just click on the sweep time. Let's go up to like 100. See what that looks like. Okay, you can see it's all a lot closer together now. What if I go down to, we were at 20, let's go down to 10. So you can see it kind of stretches it out, and I can't see nearly as much of that cam sensor. So we can just kind of mess around with the settings until we get something that kind of looks the way it's supposed to. So in this case, I like the way that looked. Now if we go over to the right-hand side, you can see the 1 and the 2, and that allows us to move the channels up and down to kind of get a little bit of separation. So let's do it like that so we can see where's the cam sensor, where's the crank sensor, and how do they match up. Now in this case, on the simulator, they're never going to match up just because the simulator is not set to put them out together. I don't know why we didn't do that, but we didn't. So it's not meant to do that. But we can still see, okay, how do they line up? Is my cam sensor falling where it's supposed to be versus the crank sensor? And I can see, maybe this gap needs to be over here. So if this gap right here, this green gap needed to be over here, then I know I'm off. My teeth are off. Right? So I could see that. Or if it is over here, then I'll know it's okay. So you just need to be able to find that known good pattern from the manufacturer. We have known good individual patterns, but not the correlation. So you can usually find that on the manufacturer's information. Okay, so that's cam and crank. Let's do one more. The ever popular CAN bus. Go back into engine and the CAN. So in this case, we'll go right to the signature test. I do need to change my signal. There we go. Scroll down a bit. It's going to tell us all we need to know about CAN. It's going to tell us about our voltage ranges, but we're going to talk more about that in a minute. And then there's my known good pattern there. Hit view meter. And then there's my CAN bus right there. Right, set the voltage range where it needs to be, set the time base where it needs to be. Scroll up, there's my known good. And then I can even overlap them a little bit more like it is more in the pattern. And there we go. We have them overlapping each other. Now in this case, we can see it all on the screen, but I'd like to get a little bit closer, make it a little easier to see. So I'm going to come down, hit those 4 arrows again. And let's go to 200 microseconds. Going a little closer. There, now we can see the whole thing on the screen, but now I can see a little bit more detail because I'm looking at less time passing. Now you see every once in a while it's glitching out. It's getting kind of wavy. It's being kind of weird. That's because of where this trigger point, this plus sign is. I'm going to move it over a little and down a little, and we'll see how it makes the signal look a little bit better. There we go. Now it's not flashing on and off the screen. It's catching it on the screen every time. So this trigger point allows us to catch the pattern on the screen. Like I said, this is high level. We go way more in depth in other classes if you want to check those out as well. Once I get it on the screen, though, I want to measure it. I want to analyze it, see what's going on with it. So in order to do that, I need to hit the stop first. So we're going to stop recording. And then I need to go up and turn on my cursors. Now it also says I can drag my graph left. So that's kind of cool. We can drag it left and right, and we can see instead of going through step by step, page by page, we can drag it left and right and see what happens. It's kind of cool. I just noticed that verbiage on the screen. I never noticed it there before, but it's been there. All right, so it's on the screen. So I want to go up here with my cursors and turn those on so I can take some measurements. Take number 1 over here, number 2 over here. And I'm going to be able to measure the peaks and the valleys. So on CAN bus, now this is a simulator. This is as close as we're going to get with a simulator. But on a real live car, These are a lot closer. Number one, this flat spot right here, this is what they call an idle state. It's a state where the bus is not transmitting data. That should be 2.5 volts on both sides. When it transmits data, remember how I said that's these blocks here. When it goes up, should go up by a volt, about a volt, volt and a quarter, 0.922. Should come down by about a volt, volt and a quarter, 1.030. So that is pretty darn close on both sides. It should match. We're really close. It's as close as it's going to get with a simulator. You want to look for nice flat tops, flat bottoms. You don't want to see any noise. If there was a glitch to ground, you would see it drop out and it would hit down here towards the bottom because that's 0. If there was a glitch to 5 volts, that'd be towards the top. 12 volts would be off the screen. On some vehicles, some manufacturers, you see over here on the right-hand side, we have this super tall one, super tall spike. Some manufacturers have this, some do not. It just depends on how they design their network language, I guess it would be. But this is what they call an ACK bit or an acknowledgement bit. So this is, I call this the period at the end of the sentence. So the computer is going to send its data. It's talking, it's saying what it needs to say, and then, okay, here's the end of my data. Whatever comes after that's not me, it's somebody else. So the ACK bit or the acknowledgement bit is, okay, this is the end, and then they acknowledge, okay, I got your information, and then they move on to the next thing. So every packet or set of data packets may or may not have that depending on the car. On the BMW, it does. On Fords, I've seen it that way. On my Subaru, it doesn't. So it just depends on how they set up the way their network communicates. So if you do see one of those, don't say, oh my goodness, it's broken. That's normal. And it would have to be at the end of the data, but that is normal. As I said before, if you want more information on any of that stuff, definitely worth your time to check out the network diagnostic class that we have as well. All right. So that is that for this evening. Let's talk about next week. So next week, we are going to get into automatic transmission controls and testing. So now we're not really talking about gears and bands and things like that. We're talking more about solenoids and the electronic components that run these modern transmissions nowadays. So we're going to talk about the different systems, how they work, how we're going to test them and diagnose them. So hopefully you can join me again, same time, same place, 6 and 9 Eastern. If you want to join on Zoom, go to snapon.com/OT. The 6 p.m. Eastern also gets simulcast to YouTube. So if you go to youtube.com/Snap-on Diagnostics, you can watch it there. Also, if you are watching on YouTube, please hit that subscribe button. Doesn't cost you anything but a click. And then make sure that you hit that little bell too to be notified next time we go live or post new videos, because I'm not the only one that does it. If you want to check out any of our previous live streams, like I said, we did really high level today, and we get way more in detail in these other classes because we had to put a lot of different things in one class today. So things like ADAS, data bus testing, component testing, we did over the summer, HVAC, things like that. So if you want to watch any of those, they're archived on our YouTube channel. Once again, youtube.com/Snap-on Diagnostics. Okay, question time. But before we do, let me talk about my buddy Al. So Al also does training online. He does training on Zoom. And he does 3 nights a week. So Monday is Apollo, Wednesday is Zeus, and Thursday is Triton. And this is learn how to use your tool better, or learn how to use your tool to begin with. So we call it platform training or scan tool training. So it's on that individual scan tool. And it's kind of designed to have yours in front of you, and you follow along with him on the computer, and then you follow along on your tool in front of that. So first hour on all the classes is pretty much the same thing. It's just on whatever the corresponding tool is. And it's let's set up your Wi-Fi. Let's make sure that's working, because there's a lot of functions on cars nowadays that we need Wi-Fi for. Some of the stuff happens in the background. You don't even realize. So we got to make sure they hook up to Wi-Fi. Then we're going to make sure you get set up with a free Snap-on Cloud account that allows you to upload screenshots and pre and post scans to be able to share it with your customers if you need to. And then also it'll go through code to completion, real world analysis of how we would use fast track intelligent diagnostics. How does this help me? Doesn't matter what level of technician you are, it will help you save time because it automates a lot of tasks you might already be doing. And it's going to be based on known good vehicles. So known good and known bad vehicles. So it's going to walk you through all that. And that, as I said, that whole thing takes about an hour. On Wednesday and Thursday, since those tools have scope and component testing, He'll also, after a 5-minute break, he gives you a little break. After that, he goes through the scope, the meter, guided component tester, all the different meter and scope functions of the tool. He'll bring you right through those on the Zeus and the Triton as well. Very thorough class. Al's been with us for over 30 years. He came over with Snap-on Diagnostics when it first became Snap-on Diagnostics. He's been with us a long time, has a wealth of diagnostic tool knowledge. So definitely check him out if you haven't already. Once again, snapon.com/OT to register for that. All right, let's check out questions. Got a lot of activity over here on YouTube. And we got a couple questions, or one question at least on Zoom. Let's see. Claude, where can I find some information to use the simulators to incorporate into classrooms? All right, so here's what I'm gonna do, Claude. I am going to, in the chat, since you're in Zoom, in the chat, I'm going to enter the part number for this, and you can order it right from Snap-on, actually. It's a little BMW. I don't know if you can see it on my screen, but it's upside down, but it's a little, looks like a BMW, but it's got all sorts of components that we can test on. And I will plug that into the chat. That's EESX. Where'd it go? There it is. 306 SP. Okay, so that's going to be to everyone. There we go. Okay, so that's the part number. So you want to write that down, copy that down. I'm going to copy that. Actually put it on YouTube too, in case you guys are interested.
Hey, Jason, just a quick reminder that that demo board comes with a very, very detailed user manual with it to show you how to set it up for different types of tests and examples.
Yes, sir, it does. It's very detailed. So you got cam and crank sensors, injector, ignition, wheel speed sensor, accelerator pedal position sensor, which doubles as a voltage tester. You got square wave, sine wave, and pulse width and CAN bus all on there as well. So let's see. Claude also says he already has a bunch of these, so that's good. So I guess you didn't need the part number, but BMW Town & Country and another. The user's manual. So if you want the user's manual, I'll put that in chat as well. So snapon.com/diagnostic or diagnostics.snapon.com. And that, if you go all the way down to the bottom of the screen on that, it has manuals, and then there is a user's manual section for both of those demo boards. So both the scanner and the scope demo board. So very good, very thorough, like Al said, very thorough manual on both of those. So definitely worth checking out if you want to get a little bit more schooled up as to what's going on with those. Check YouTube here. It's kind of Mike's in the middle of my screen, but Abel, welcome. Thanks for checking in. I saw you check in early before we started. Thank you for that. Richard Gill, welcome. Thank you. Nick, welcome from the UK again. Let's see. GIE Auto. Yes, it is great to see what the PCM is looking for before processing. It's always best to verify that signal is working before it gets there. Let's see. Nick also says he uses his scope on his Zeus to carry out battery tests on customer vehicles. Perfect. Perfect. Casey, good afternoon for you. Good evening for me. You must be probably further west than I am. Let's see. Nick loves the free training. Thank you for that. I see we have some Russian friends in here too tonight, but that's okay. And let's see, Raymond. Yep. Thank you again for checking in there, Raymond, as well. So with that, looks like we cleared the board there. And don't have any more questions. So thank you very much for that. Always able to clear those out. Thank everybody for checking in and saying hi. It's always glad to see everybody. And I always want to thank you for taking a little bit of time out of your busy week, your busy day. Come spend a little bit of time with us. Hopefully you get a little bit better understanding today of why we want to use multiple channels to have correlation between multiple channels so we can see what's going on the same time base to be able to see how things are reacting with each other. Hopefully we'll see you next week for automatic transmission electronics, and enjoy the rest of your week. Enjoy your weekend. Hopefully we'll see you next week. Take care.